All right, everyone. I think I'll just go ahead and get started. I want to review Monday's exam. So today is the 12th. So did anybody get a chance to look at the problem set? Is it accessible?
Yeah.
It is? Okay. I found a mistake in it, so can you, Josh and the others, can you print out a newer version? I just forgot to put some constants in there.
Okay.
All right, so, and make sure that's accessible. If you don't have access to it, immediately text me or email me, and I'll make sure everything is okay. So it should be available, but I just looked at it like at 11 o'clock this morning, and there's one problem where I forgot to put some constants in there. So it's the heating, cooling problem. I'll go over that along with some other things. First, let me go over the multiple choice portion of this exam that should be available on Monday. One of the multiple choice questions has to do with vapor pressure. So what do we know about vapor pressure? If you want to exert a lot of vapor pressure, okay, a high amount of vapor pressure, what does that mean in terms of your intermolecular forces? Okay, do they have to be weak or strong? Very good, they have to be weak, okay? Remember, vapor pressure, forming a vapor. If you have to overcome hydrogen bonding, which we consider strong, then you're not going to form a vapor. So the key here is the higher the vapor pressure, the weaker the intermolecular forces that you will have. The weaker the intermolecular forces. So as an example, let's take an alcohol, okay, like an ethanol. Let's take an ether. And let's take an alkane, okay? Okay, do we know our functional groups? Ethanol is what we will call an alcohol. Okay, so you can use that sheet I sent out, or I printed out. Okay, do we know what an ether looks like? Okay, ether looks like this with an O in the middle, oxygen. And do we know what an alkane looks like? It's just basically a hydrocarbon, right? Like your methane, ethane, propane, etc., etc. So the question here is, which do you think would have the highest vapor pressure? Highest. The alkane, the ether, or ethanol? Highest. Okay, remember the rule here. Okay, it's kind of tricky. Which one would have the highest? I would rank it number one. Highest vapor pressure. Okay, what holds together an alcohol? The OH? Hydrogen bonds. Okay, can an ether hydrogen bond? No, but it is polar, right? Is it polar or non-polar? Polar. Okay, what holds together an alkane? Methane, ethane, propane, hexane. Dispersion forces. Okay. All right, so which is the weakest of them? Weakest would be alkanes or dispersion forces. Which would be strongest amongst these three? Hydrogen bond, and this would be kind of in the middle. So vapor pressure. Okay, which would have the highest vapor pressure? Which would like to go boom? The alkane. So I'm going to label that 1. Okay, which would have the second highest vapor pressure? Even though this is polar, this would still have the second highest vapor pressure, and then which would have the lowest? Well, what's left over would be the, low. What's left over is the hydrogen bonded one. So, functional groups, ethanol would have the lowest vapor pressure. It just doesn't want to form a vapor. If it does, It just takes a lot of energy to form a vapor. All right, so that's one of your multiple choice question themes. Okay, by the way, let's rank these. What would be the strongest intermolecular force that we studied? Okay, stronger than hydrogen bonding.
Ionic.
Ionic, very good. Okay, that is just a full, I'm positive, Robert, you're negative, so we really get along together. Opposites attract, don't they? Okay, what would be second strongest? The hydrogen bonding, very good. Okay. Even though hydrogen bonding is polar, I want to ask you what three things make up a hydrogen bond? Look for these three. I heard it. Look for OH. Look for an NH anywhere in the molecule. And where else? What do you see? We don't see this a lot in biochem, but in chemistry we do see it. Fluorine. Fluorine is not really found in our body a lot, but in other chemistries that the other professors teach, fluorine, anything with a fluorine has the potential to hydrogen bond with a hydrogen somewhere else on the molecule. It could be its own molecule. Remember, water can hydrogen bond to itself. Something can hydrogen bond to itself. All right, so first, second, and then what's third? Right, polar or dipole, very good. Okay, we call that a polar molecule. It has what I want to say is a net dipole moment. Okay, what is the weakest? Dispersion, okay. Dispersion is the weakest. So we associate dispersion with two things. We associate dispersion with the alkanes, methane, ethane, propane, hexane, pentane, octane. We also associate it with nonpolar molecules. Okay, molecules that have no net dipole moment. Okay, nonpolar molecules. Example would be CCl4. Okay, a nonpolar molecule. So those are the two things associated with dispersion, and then you guys are right. Okay, we go from here, the strongest force to the weakest force. So I'll have a copy of this at the end of lecture. Just want to move on. We only have 50 minutes or so. The next thing here is miscible or not miscible. Okay, so here we're asking ourselves the question, can it mix? So here, again, you want to use like dissolves like. All right, so I'll give you 5 examples here. You tell me whether they can mix or not mix. Okay, how about NH3 and water? Okay, NH, this is called ammonia, by the way, NH3 and water. Do you think, will they mix or not mix? Okay, do you guys agree they can mix? Okay, NH3, the NH can hydrogen bond. Water, OH, and its structure can hydrogen bond. Okay, what about this one here, CCl4 plus water? Will that mix or not mix? CCl4 and water. Water is polar. CCl4 is nonpolar. It has no net dipole moment. So immiscible, no mix. How about this one? KOH plus water. Potassium hydroxide. Mix or no mix? Mix. This is ionic. Okay, potassium ion and hydroxide ion. Water is polar. This would be ionic with the polar, so mix. Very good. How about KOH plus carbon tetrachloride, CCl4? Mix or no mix? No mix. KOH is ionic, potassium ion, hydroxide ion. CCl4 is nonpolar, so no mix. Okay, this has no net dipole moment, CCl4. How about CCl4 and CS2 carbon disulfide. Mix or no mix? Very good. The answer is mixed. This is nonpolar, and CS2 carbon disulfide is nonpolar, right? We know the structure. Okay, so the sulfur is going to pull in equal and opposite directions, cancel each other out. And the CCl4, also the Cls will pull in opposite directions. The arrows cancel each other out. Both of these are nonpolar. Both of these will mix because of like dissolves like. All right, what about viscosity? Okay, what about it? Viscosity is kind of like your molasses, kind of like your syrup. Okay, what viscosity is really defined as a resistance to flow resistance. Again, think of your maple syrup. Think of your glycerol if you ever worked with glycerol. Think of antifreeze if you ever worked with antifreeze. How do you identify a molecule that's very viscous from a list? Okay, look for OH. Okay, the more the OH groups, the more the hydroxyl groups, the more viscous it will be. Okay, like a glycerol. Okay, sort of thing. So the more OH groups, the more viscous it's going to be. Just a couple of things to keep in mind when you take your multiple choice exam. Phase diagram. Okay, do you guys remember this? It's a combination of P and T. P stands for pressure, T stands for temperature. Okay, P stands for pressure, T stands for temperature. It kind of looks like this. Okay, we have three phases. Anybody remember what this phase is? Phase A, is it solid, liquid, or gas? Solid. Phase B, solid, liquid, or gas? Okay, vapor or gas. And then phase C would be liquid. So be able to identify solid phase, liquid phase, or a vapor phase. What's interesting is that water in the solid vapor line has this, it bends backwards. Okay. Other substances, this line doesn't bend backwards, it bends kind of more straight. So that's what makes water very unique. Okay, for water, this is very peculiar. But of course, water is a very peculiar substance. Right, so make sure you review the phase diagram. Okay, what's the solid, what's a liquid, what's a vapor? Obviously, we have things in the line that sort of straddle the two phases. So if you're on this line, you're between solid and a liquid. Okay, if you're on this line, you're between a gas and a liquid, vapor and a liquid. If you're on this line, you're between a solid and a vapor. So you actually have two phases if you're at this temperature and pressure. B and C be switched. High temperature, high pressure. Yes, B and C should be switched. I'm sorry. Yeah.
I feel like that's some extra critical ones right there.
So high temperature, very high pressure. Are you sure? High pressure, high temperature.
So high temperature would be a vapor, and then
High temperature and high pressure. Okay, high pressure. Low pressure, high temperature. Right, okay. Yeah. So this is correct. So part B is actually a liquid. Yeah. All right, thank you. Sometimes my brain doesn't work. Majority of the times it doesn't work. All right, so whatever it may be, make sure you can identify this, what's a solid, liquid, and a gas in a phase diagram. Okay? All right, you'll have this also in your written portion of your exam. Okay, this equation, I'll give you the equation. Okay, so 1 over T2 minus 1 over T1. All right, so this equation will be given. You'll have it in the multiple choice, and it's also in the written portion of the exam. So for that one, I'm going to ask you to show your work for partial credit or full credit. All right, so do we know how to do this? All right, so let's say your P1 is 440 torr, and your P2 is 760 torr. And it's, remember, pressure and at a specific temperature, so let's call this 20 degrees, and then we have to solve for T2. Okay, so a problem like that on the exam, and you'll be given a delta H VAP. 26.0 kilojoules per mole or something like that. Okay, I'm just throwing numbers around. Alright, so being able to solve for T2 is such a problem. Okay? Be able to solve for T2. Also, 760 torr is the same thing as 1 atmosphere. Alright, so make sure you know that. 760 torr is the same thing as 1 atmosphere. And also know that this is sometimes called, if your pressure is at 1 atmosphere, and you boil, that's called the normal boiling point. Or normal melting point. Normal whatever. Normal means your pressure is 1 atmosphere. So when I say normal boiling point, what is the pressure? 1 atm, 1 atmosphere. Okay. Normal melting point, normal freezing point, what is the pressure? 1 atmosphere. Anytime you see normal, what is the pressure designation? 1 atm, 1 atmosphere. Good. Okay. So just want to make sure you know that. Okay, if you see that on the exam, normal means 1 atmosphere. All right, if we have time at the end of class, we'll go over this type of problem. One thing I should tell you, the first thing you should do is, one thing is I'll give you R, so that's given. So that constant is given. One of the first things you should do is convert this to joules over mole to get the units to cancel. You want to convert your delta H VAP, vaporization, to joules over mole, and that is just simply multiplying this by 1,000. Okay. And then you can start plugging stuff in. Okay, so that's step 1. Okay, don't just put in kilojoules per mole here, because the units will not, you'll be off. The units will be off, and that's not the right way to do it. You want your units to all come together properly. Okay, so don't just plug it in. Convert your delta H VAP to joules per mole. couple of other things for your multiple choice. All right, I think we kind of covered this up top, but let's go over it again. If you have a low vapor pressure, okay, what does that mean in terms of your intermolecular forces? Strong or weak? Strong. So maybe something like a hydrogen bond or ionic. Something that's ionic will not really form a vapor pressure. Do you think salt, which is ionic sodium chloride, has a vapor pressure? No, it's basically a solid cubic lattice. So low vapor pressure, hydrogen bonding, basically strong intermolecular forces. What will that do to your boiling point? High or low? BP, boiling point. Somebody said high? It will have to be high. Very good. Okay, so that's how you want to think this through. And I feel like you got it. Okay, high boiling point. Okay, you need to add, as Adriana said, a lot of temperature, energy to break apart these hydrogen bonds, and they're not going to form vapor on its own. Okay, so that's one pipeline, one flow chart. Okay, the other one is the opposite. Okay, so high vapor pressure. Okay, weak intermolecular forces. By weak, we're probably going to be talking about dispersion or something that's nonpolar. Your alkanes, your carbon tetrachlorides of the world, okay, your nonpolar molecules. And obviously that's going to have a low boiling point. Okay, this BP stands for boiling point. All right, so if there's a high boiling point like water, okay, obviously that's, which is 100 degrees C, you know that water can hydrogen bond, and you know water, relative to other molecules, this is all relative to others, will exert a very low vapor pressure. And speaking of vapor pressure, what do we quote vapor pressure at? Vapor pressure is quoted at a specific T temperature, right? Vapor pressure is quoted at a specific temperature. Okay. So as an example, and we usually look these up in a book. So H2O at 25 degrees C has a vapor pressure of, again, I looked this up, 27.6 millimeters of mercury. Okay, if you raise the temperature, okay, you'll have a different vapor pressure. Actually, if you raise the temperature, you'll have a higher vapor pressure, more vapor as you increase the temperature. So vapor pressure is quoted at a specific temperature. All right. Raise the temperature, more vapor pressure. In fact, it looks like this. It kind of looks like this. Okay. Vapor pressure on the y-axis, temperature on the x-axis. That's the profile. And if we look at the vapor pressure here at 1 atmosphere, at 1 atmosphere, this temperature is called the normal boiling point. The temperature is the boiling point, and it's also the normal boiling point. Okay. P is equal to 1 atmosphere. All right, multiple choice question. The 4 properties of a liquid. You guys, can you 4 properties or 3 properties of a liquid? You guys remember them off the top of your head? Four properties of a liquid. I'm sorry, not 4. Well, it could be 3 or it could be 4. Some of them, there's one that we group together, so I'll just call it 4. I say 3, then I say 4 because cohesion and adhesion sometimes get grouped together. Okay, so that's one. What's the other one?
Surface tension.
Surface tension, very good. Okay. Surface tension is kind of like at the air-liquid interface. Your lungs actually are an air-water interface. At the interface, the liquid molecules are a little bit stronger intermolecular forces at the surface. We call that a surface tension at any interface. So this would be the liquid, and this would be the air. Right here, surface tension. The molecules have a stronger intermolecular forces. A little bit stronger. Little bit stronger intermolecular force right at that surface. And then what's the third one or fourth one?
Viscosity.
Viscosity. Okay, resistance to flow. Some liquids can flow better than others. Okay, and those that have viscosity tend to have more OH groups. Bless you. For more hydrogen bonding, they tend to have more OH groups. So those are the 3 or 4 properties, okay, depending if you want to group this together, of liquids. All right, okay, how about this one, colligative properties? This one definitely has 4. Can you guys name them? Okay. What happens if you add a solute to a solvent? Okay, 4 things happen when you add a solute to a solvent. One of the things we do is we make a solution, right? Solute plus solvent is a solution. So we make a solution when we add solute to solvent. But what 4 fundamental properties happen once you make a solution?
Freeze point.
We have a new freezing point. Will that go higher or lower? Lower. Okay, so hopefully you'll see that in this lab today or next week. Freezing point depression. We have a new boiling point. Will that be higher or lower? Higher. Okay. We have a new vapor pressure. Will that be higher or lower? Vapor pressure. We have to overcome solute and solvent interaction, so it's going to be lower. And finally, for biology majors, what happens in the presence of a membrane? What will you get? Okay. We get an osmotic pressure if you put in a membrane, okay, in the presence of a membrane. So, 4 colligative properties, they're universal. It doesn't matter how much solute you add. It doesn't matter how heavy or how light the molecular weight of the substance is. This is universal, okay, once you make a solution. All right, speaking of vapor pressure lowering, okay, let's do a problem here. Okay, first of all, the equation is this for vapor pressure lowering. The equation is the new vapor pressure of the solution is going to equal, this is called the mole fraction of the solvent, times the vapor pressure of the solvent alone. Okay, so that equation will be given on your exam. So let me throw out some numbers for you. Let's say I take 10 grams of glucose, C6H12O6, it's glucose. Okay. And I put it in 125 milliliters of water. All right, and obviously vapor pressure is quoted at a specific temperature, so we'll make this room temperature at 25 degrees. Again, I'm just throwing some numbers at you guys. So a typical problem would be, what is the new vapor pressure of this glucose water solution, which is solute plus solvent. Okay. So do we know how to solve this problem? I should also tell you that vapor pressure of water alone at 25 degrees C, again, we look it up, is about 23.76 millimeters of mercury. Right. Are you guys able to solve such a problem? Well, the vapor pressure of the solvent alone is here, so that's going to go here. How will we calculate the mole fraction of the solvent? Okay, so this is the moles of the solvent divided by moles of solute plus moles of solvent. So anytime you have to deal with water, I just memorize this. The density of water is about 1 gram per mil. Okay, at room temperature also. So just keep that as a memory. Density of water at 25 degrees is 1 gram per mil. Okay, so maybe good to memorize this. 1 gram per mil of water, its density at room temperature. So we can get our moles of solvent, which is water, okay, by taking advantage of our density. All right, 1 mole of water is about 18 grams of water, again, using the numbers from the periodic table. So I did not solve this, so so that's going to be your moles of your water. So that's going to go here. Okay, it's also going to go here. And then the mole of solute glucose is very easy to find, okay? And that's 10 grams of glucose in the problem. Times 1 mole of glucose. I think this is about 180 or so grams. 6 times 12, 12 times 1, and 6 times 16. So add them up. It's about 180.04 or 0.04 grams of glucose. So this will equal to the moles of glucose. We can put that here. And this is how we'll solve this problem. All right. All right, the last 15 minutes or so of class, I'll like to go over maybe 3 more problems, math problems. One of them has to do with mole percent. Okay, mole percent. Oh, by the way, there is another problem that has to do with units. Okay, I'm a big guy on units. So what are the units of small m? What are the units of big M? Big M is molarity, so moles of what over what? Big M molarity is moles of solute over liter of solution. What is the small m? Something we learned that's kind of new in Chem 2. Molality, very good, which is moles of solute, but this time it's over kilograms of solvent. Okay, we call that molality. So units. Okay, units of concentration. Okay, units of concentration. You ever get blood work done? Okay, all of those units are in units of concentration. Here, I'd like for you to learn 2 units of concentration. One is called molality, and the other one is called molarity. Okay, concentration. All right. Here's a problem that involves mole percent. So let's say I have Let's say I have 7 grams of sodium chloride. Okay, and I dump it in 100 milliliters of water. Okay, remember, I want you guys to memorize this. Okay, not just for this exam, but maybe in your future career. Quick and dirty, at 25 degrees, this is about 1 gram per mil density. Question is, what is the mole percent of NaCl? Okay, another type of concentration, mole percent. So how will you solve this problem? Okay, mole percent of NaCl is the mole of NaCl divided by, it's a percent, which means it's a fraction, divided by part over whole, mole of NaCl plus mole of what else? Water. Okay. To get it as a percent, we have to do what? We have to multiply it by 100. Okay, to get it as a percent. Okay, so take the 7 grams, convert it to moles. One mole of NaCl. I don't know what is it? 58? 58.01 grams of NaCl. Okay, that will give you moles of NaCl. And then the moles of water you can use the density, right? So 100 mils of water times 1 mil is that many grams density, and 1 mole of water is about 18.01 grams of water. And you should have everything that you need to get the mole percentage of solute sodium chloride. Okay. All right, 2 more problems in the last 10 minutes, so let's see if I can finish that off. One of these is the dreaded heating problem, heating, cooling curve of water. Okay, so let me tell you how we do this. So let's say I have 200 grams of water, and it's at minus 70 degrees C. Okay, very, very cold, minus 70 degrees C. And I want to heat this water. I want to heat this 200 grams of water. I want to heat it to a temperature of 125 degrees C. Okay. So the question here is how much heat is required to heat this water? How much heat is required to heat? How much heat is required to heat? How much heat is required to get from minus 70 degrees C to 125 degrees C? And we're dealing with 200 grams of water. All right, so this is on your written exam. It's a very long problem. So definitely take a lot of time to do it. Again, you have the weekend. Let me tell you how you do it. You want to split this. Okay, you want to split this. Okay, don't just put in the equation Q equals ms delta T. Okay, you want to split this. You want to split this into 5 parts. Okay, and add the heats. The first part, you want to split it in going from minus 70 degrees C to 0 degrees C. Okay, minus 70 to 0 degrees C. And here you will use Q equals ms delta T. Okay, the S here is for ice, and I think I give it to you in the problem. It's about 2.093 joules over grams degrees C. That's for ice. So you're going to get that Q. All right, now we are at 0 degrees in our heating. Okay, what happens at 0 degrees? Okay, something called a phase transition happens at 0 degrees. So we have at 0 degrees what's called a phase transition. So the phase transition, you have to add the heat of fusion. Okay, whatever that number is, I'll give that to you on the exam. But looking this up before I came here, it's about 6.010 kilojoules per mole. Okay, make sure you get it to joules per mole. Make sure when you add up your units, they all are okay, right? Kilojoules here for your constants. All right, once we overcome 0 degrees in our heating from minus 70 to 125, we're at step 3. And at step 3, you want to go from 0 degrees to 100 degrees. Here you're going to use Q equals ms delta T. And here you will also use the specific heat of liquid water, which is about 4.184 joules over grams degrees C. Again, I will give you the constants. Okay, I will give you the constants. We don't memorize constants in this class. All right, so we went from minus 70 to 0. We added more heat to overcome the phase transition, shown in blue. And now we have to add heat to go from 0 to 100. And now we're at step 4. At 100 degrees, we undergo what's called a phase transition. Here we have to overcome delta H vap. delta H vap, or delta H vaporization, and I'll give this number to you. Delta H vap is about 40.7 kilojoules per mole. Again, check out your units. Here we got kilojoules per mole, and here on your constants we got joules over grams degrees C. So we need to keep our units consistent. And then finally, we've overcome 100 degrees, we've overcome delta H vap. We add our final heat, which is going from 100 degrees to 125 degrees C. Here we're going to use Q equals ms delta T, and our constant here is water, but water in the form of steam. See, right here we're at steam. Right here we're at liquid. Right here we're at ice. And right here in step 5 we're at steam. And I looked this up before coming here. For steam, the specific heat constant S is 1.99 joules over grams degrees C. All right. So you're going to have to add up Q1, Q2, Q3, Q4, Q5, and you're going to have to make sure the units are consistent. Okay, I've seen situations in the past 5 years or so where the units are all off. Okay, and remember, you're dealing with 200 grams. Okay, 200 grams is not the same as 1 mole. 200 grams is not the same as 1 mole. This is for 1 mole. 200 grams is not the same as 1 mole. This constant is for 1 mole. So what do you need to do? Convert this to moles, okay? You have to convert to mole to get the units to cancel. So a lot of steps where you could potentially go wrong here in this problem. So check that out. Because of time, I am not going to talk about this further, but I will go over one final thing here. Okay, in the last 5 minutes of class. Okay, let's say you have 20% by mass HCl, hydrochloric acid. Okay, and I tell you the density of this hydrochloric acid is 1.098 grams per milliliter. That's its density D. And the mass percentage is 20%. Okay, so 20% by mass HCl is the concentration. Density is this. This is given in the problem. So question to you guys is, what is the molality, small m, and what is the molarity, big M? All right, so 20% by mass. HCl basically means we have 20 grams of HCl over 20 grams of HCl plus how many grams of water? Okay, 80, because it's a percentage. All right. So we can convert this HCl into moles. Don't forget our solute is HCl, our solvent is water. So let's convert this to moles. 20 grams of HCl, 1 mole of HCl is about, I don't know, 36.01 grams of HCl. Okay, using the periodic table. So this gives us the moles of HCl. Okay. By the way, what is molality? Moles of solute over kilogram of solvent. What is molarity? Moles of solute over liter of solution. A liter of solution. All right, I know I'm rushing, but I just want to complete this. This should be recorded and up by tonight. So the moles of solute here, we have it. Okay, how will we get kilograms of solvent? How will we get to kilograms of solvent? Okay. Right here is our kilograms of solvent, so that is dividing it by 1,000, 0.080 kilograms of our solvent. So now we can solve for molality. So I think that's easy enough. How will we get liters of solution? Okay, how will we get liters of solution? Well, how many grams of solution do we have? How many grams of solution? 100 grams of solution, 20 grams of solute, 80 grams of solvent, 100 grams of solution. Of HCl. Okay, we know the density is 1.098 grams per mil of solution. And we know that for every 1,000 milliliters, there's 1 liter of solution. And you notice here the grams of solution cancels with the grams of solution. The milliliters cancels with milliliters. And that should give us our liters of solution. And that one can go right here. So we have all that we need to get the molality and the molarity given the mass percentage of this HCl. So that will be pretty much your exam, what to study for and what to look forward to. So Josh, please download the new version of the written exam. It should be, I made some changes to it, particularly with regards to the constants. I hope it's right. If it's not right, you can email me. I'll be available Sunday night. Okay, I'll be available Sunday night. And you can see me through Zoom. All right, I will let you guys go. If you're going to do the lab, Larissa will be there. I have a meeting to go to, so I'll stop by if the meeting ends. All right, I'll see you all on Monday. Please come to class Monday and turn in your quiz Monday. Okay, upload your quiz, unless you want to make it your drop. Have a good weekend if I don't see you guys again.